There's going to be a lot of overlap here between sections 10.4 and 10.5. Both sections are dealing with deciding whether or not series converge and finding the interval of convergence for those series. So all of these are, when we talk about Taylor series, which is what we usually deal with, remember that Taylor series are a type of power series. And so in general, when we deal with power series, there are three possibilities for convergence. The first is that a series only converges at one point, that x equals a, the center. Uh, this is the minimum interval for every power series. No matter what, a power series will always converge at its center. Uh, the distance for x's that the radius converges is what we call the radius of convergence. So if our series only converges at x equals a, the radius is 0 because the distance from the center is 0 that actually works. A second possibility is that series converges for every x. In other words, our radius is infinite, which would be all reals. And then the third possibility is that our series converges as long as x minus a is less than our radius. And this is what we get used to talking about, like with our geometric series of saying that for 1 over 1 minus x, this only works if the absolute value of x is between negative 1 and 1. In other words, the absolute value of x is less than 1. Our radius would be 1. The thing where these get a little more complicated is if we're sitting there, we will need to learn how to check to see does the series converge at the endpoints when the absolute value of x minus a is equal to the radius, because sometimes they do and sometimes they don't. And what we'll be doing over the next about a week and a half here is going through a lot of different tests for convergence. And this flowchart I'll be giving to you on Tuesday in class, but it kind of goes through from easiest to most difficult in terms of our tests. Some of these we've actually worked with, we just haven't given a name. Some of them we haven't. The one I want to kind of mention here right now is we have briefly mentioned that if we do the sum of the absolute values of the terms and that converges, then the series without the absolute values also converges. And that's something that we take advantage of a lot with all of these tests. Uh, but then, sorry. The one test I want to discuss in this video is the ratio test. Uh, I personally like this a lot. I use it a lot. Of the different tests we're going to be learning, this is probably the most commonly used. And uh, it's used so for several reasons. One, we're comparing one term to the next term. And this means that we're actually looking at, if it were geometric, we'd be finding what the r would be that would give us one term to the next term. But the idea is I take the n plus first term and compare it to the nth term. Uh, if this is less than 1, our series converges. If it's greater than 1, our series diverges. If it equals 1, this is what we call inconclusive. It means it might converge, it might not. We actually need to use a different test. And a lot of the time, what's going to happen is we're going to end up doing this with absolute values. So we would actually be looking at the limit as n goes to infinity of the absolute value of the n plus first term compared to the n, or the absolute value of this. Because we're going to take advantage of what we did way back in section beginning of this chapter, where we said that if a series converges with just the absolute values, then it must converge for everything. The next video, I'll go through some examples of actually doing this ratio test.